Thursday in April of 2023. Quite sunny and a warming afternoon. If it's already 70, 75 degrees before May, one imagines that it'll hit 100, 110 this summer. So I've been reading this Albert Einstein's Out of My Later Years, and last time what was read was a particular chapter 10, and what chapter 10 is about is relativity. And in it, Einstein offers his definitions as of, in his later years, how he felt personally and explicitly and statedly what the definitions of relativity were. And he made, as was noted in the grandiose hedge, in the abstract ideal of the grandiose hedge, that it's inclusive of things and also restrictive of things. So it's inclusive of things that's meant to cover and absolute and unbounded in a sense, and the restrictive of things that he very clearly defines that relativity is the absence of absolute motion, not absolute space, but absolute motion. So that we have basically the displacement over time has the displacement in time, those complementary quantities, end up being disconnected in the sense that then what regards end up being length contraction and time dilation equaling space contraction can be a thing, as it really well is in all matters of the motion of the bodies, the objects through space, and especially in their dynamics. The statics in physics are things of at rest and undisturbed, and the dynamics of physics are those things that interact and see the emergence of what follows from the principle of least action, that there is a sum total of all the actions which comprise the events and arrive at that parallel transport as a thing. And the instanton and the soliton are concepts for then the acoustic notion, the phonon, and then for light's particle, the photon, and that for the phonon and the photon, that these models of waves in various media have mathematical models that have physical interpretations of what are physical models, and thus via these representations we can associate them with empirical things, or those things available to observation and observable quantities, and also the reproducibility of experiments, or the idea that all else same, that any two physical experiments should result the same. And anything else indicates that the model is at best incomplete and at worst falsified and otherwise subject to some contrivance. So these are the kinds of things then that Einstein built for us, a grandiose hedge of sorts, that what results is for relativity then, in the L principle, that light speed is a constant in deep space, in a vacuum, very, very, very far removed from everything, at absolute zero, with all these other particular conditions that might affect the transmission of light, its energy, and also light, its optically its image, as a continuous signal with a continuous tone image, that it's as well to read that and understand that it's as for Lorentz, and that his laws of nature are only so contained in the mathematical model, that his laws are mathematical laws in relativity. And then also that there was a very much appreciation paid to what he left out in terms of that he doesn't try to establish that there's one or the other, length contraction, time dilation. He doesn't try to establish that what's composed cannot be decomposed. And there's these sorts of things that make for Einstein, and after his many, many years of research into his total field theory, which is what he called his idea of his true physics, that relativity and special and general relativity are laid out, and it was discussed how general relativity has that special relativity's derivations follow instead of the other way around. For some people, that these days that's called that SR is local because there's non-local phenomena. Because about Mach's principle of the global and total, that these are the basic keys with regards to a theory of sigma potentials or theory of omega potentials for a special unitary group in infinite dimensions in SUN gauge theory. That Einstein's theory was well laid out in chapter 10. So then there was a couple paragraphs right up after chapter 11 about E equals mc squared. Now, if there's one most famous physicist in the world, who's Einstein, then there's one most famous formula of physics, and it's E equals mc squared. And what it represents is that if there's a universal quantity in physics, it's energy. And if there's universal action, it's either the transmittal or the conversion of energy. And so if that's to be one or the other, then it would be conversion of energy, including that energy naturally has forms which affect restitution and oscillation and dissipation and attenuation. And all such laws of physics, like the first and second thermodynamic laws, which are different. Why? Because of ones with respect to 1 and the other ones with respect to 0. And then about things like the other tendencies towards entropy, which is the disorganization state, that with respect to that as the emergence of any dynamics results a dynamical system, and the formation of higher order structure, that there's as well this otherwise general attenuation in effect, that light in its dispersion follows this general sort of dissipation and attenuation, and so does sound, and all these other quantities which emit some sort of omnidirectional energy, which result its saturation into the floor and the depths of things, all that surrounds. So E equals mc squared was arrived at as a formula. And how it was so arrived at is that there was an expression for the kinetic energy. And the kinetic energy was then written in a form called a Taylor polynomial, or an expansion in the order of m, and in accordance with c squared. And so given that the kinetic energy equation had this infinite sequence of terms in higher and higher and higher orders of this that would be in the units of energy, you know, the units of energy, that squared, that or cubed and to the fourth and to the higher order series elements of the Taylor expansion of the kinetic energy equation, that this simple rewriting and its truncation after the first term, the lowest order term capturing most of the amount, reflected then that was also pretty close to what was released in various conversions of matter to energy. There aren't too many real conversions of matter to energy, except of course it's a constant process. The sun is powered by fusion, as far as theory says. Hydrogen fuses to helium in this solar furnace of that's thermonuclear reaction, and it releases energy, and that energy both fulfills keeping it going, and because it establishes conditions for thermonuclear fusion, and also it releases all the rays and what results anything else that arises from the sun and its stellar pulsation as a medium-sized star of sorts, and one we're so lucky to call part of home. And so then other examples, which are a little bit more accessible in the laboratory, for example, include things like thermonuclear or fission reactions, which are thermonuclear in the sense is that the fission of materials that have a short half-life respectively to the time that they can be observed and measured in the laboratory will result that according to how much of some of these radioactive materials are involved and what can be used to assemble them into a critical mass, whereas after neutron bombardment, or in terms of media that concentrates what results after the emission of nuclear radiation, nuclear bombardment of the neutrons, that such matters then see that in these particular, accordingly, conversions of matter to energy, that E equals mc squared adds up. And so most people familiar with the E equals mc squared are familiar with the idea of, well, that's what made it possible to compute how to make an atom bomb. And this is where the nuclear fission is one of the mechanisms by which a great result of energy can be converted in a small area. and thus it results that E equals mc squared is deemed a very powerful equation. But really, it's a very straightforward application of these mathematical methods from what are the attachments of the models, and then these equations in terms of the kinetic energy in terms of a collision, that series was just written out and the first term picked off, and then it was said that was an approximation for the amount of energy in terms of m and c squared, in terms of the velocity of this thing with respect to c squared, as with regards to that being this release of what's plain energy in terms of what's otherwise the Massian kinetic. It's massless energy in terms of the thermo first and second laws, and in terms of all the other aspects of physics that comprise for us what's called the gravity, the strong nuclear force, electricity, the weak nuclear force, and electroweak force. Those forces then defining the fields that in all their potentials add up to all manners of nuclear reactions, including chemistry, including radiochemistry, including magnetochemistry, including all such matters of the transmutation or lack thereof of matter that result these physical states of matter and all their states and their transitions of states and all this stuff that then in a usual setting left undisturbed results attenuation towards entropy, if towards a floor. When the universe is studied and you look out at all the stars, Olbers' paradox is, if the sky is full of stars, why isn't it bright all the time? Well, because it's not that bright by the time it gets here. It dissipates and attenuates. Well, if the sky is so black in the coal sack of where the stars aren't, why don't we freeze? Well, there's a remnant or cosmic microwave and also an infrared background radiation. So it's not so much optical, it's just kind of both infrared, which surprises a lot of people and is not predicted by certain theories, but is found evident, and microwave radiation, which cosmology kind of has as, the remnants of the Big Bang, but otherwise would be just, that's where all the rest of the stars' energy is in the floor. So that the stars, these pinpricks of light, and these twinkling candles, and the background radiation are neither all black and white. Then there are gravitational singularities that result the absorption of all information in terms of their gravitational singularity, and they're called black. And then there are white holes as a general notion of various kinds of singularities or anti-singularities of a sort, and that these might be considered omnipresent, or that the origin is everywhere, just like Einstein's coordinate origin never is absolute with respect to the moving frame and the absolute velocity, that it's relative, the velocity to anything else relative its velocity. Similarly, these origins everywhere are each just their own frame, that every point in space-time is a frame. Then with regards to its contents, the frame established by the rotational and the linear, the moving frames. These are the sorts of things that establish above these dualities of things, the necessary need to result how it's possible to disambiguate these things so that velocity is displacement over time, is as well all the accelerations to add it back to rest. Otherwise, to implement the accelerometer is relative to the frames it's in. So E equals mc squared is E equals mc squared plus dot dot squared in the terms in order, plus dot dot cubed, plus dot dot dot, all the following terms truncated. And it's not just truncated because they're immaterial to it. I mean, mathematically, they're part of the same equation, and this value is very close, but it's not perfect. It's an approximation. It's not a pure formula even of the mathematical models. It's a result of a numerical method applied. Then, insofar as where, from one point of view, like spatial relativity and locally, you can kind of see that as the first term. As far as general relativity is concerned, it's followed by appended what would be nonlinear terms, or these some terms of potential, that don't even really have the same units. And so in terms of our dimensional analysis, lead out to this, what are called multipole moments, and after the 4 vector and the bivector, or these kinds of things that get into, for example, as there's been much reading here about the nonlinear analysis and harmonic theory and the path integral, why the mathematics of these things are so interesting and special, because somehow they fulfill these supermodels, super classical models of flow, for flux as the tachyonic and flow as the bradyonic, and the superclassical, which results for supersymmetry, supergravity, superconductivity, and this, the supersingularity of a gravitational black hole, or as examples, that these are the kinds of things that are real. And so then why our mathematics has arrived at what it is, from the discretization, from after the ultraviolet catastrophe, from the discrete orbitals and the energy so involved, in terms of that being over time and in bulk, and vis-a-vis when it's established in the very small, and the conditions and configurations of experiment, which do affect AFFECT, the measurement and sampling and observer effects, EFFECTS, that do affect the effects in this manner, such that it's been a long time coming to put those pieces back together, because the superclassical is not necessarily so intuitive. But the idea that the universe results all superclassical is pretty intuitive. If it's infinite, for example, to start, that's already superclassical in numbers. If there's a continuously divisible time, like after Zeno's paradox is that there's no smallest such quantity is a thing, that what we have is the smallest quantity is Planck length and Planck time, or so. Although I'm not quite so sure about Planck time, but that Planck length is arbitrarily small. It's smaller than an atom, as an angstrom is smaller than it's smaller than an angstrom is smaller than an atom, or along those lines. And it reflects the limits with regards to any kind of optical or microwave radiation, and being able to, according to Heisenberg and Schrodinger in the pictures, establish observables on these things. If that's not small enough, because it's still not infinitely fine, it's still not smooth in the grain, it's just very, very small, and small enough that it's effectively infinite, any collection of higher order things. Just like an Avogadro's number of things is 10 to the 23rd power, arbitrarily large number, and bigger than any grain of sands of the whole earth or something like that. It's arbitrarily large, arbitrarily small. That then is the idea of the superstrings theory is, well, we need a continuous background from that, but we still have to keep things discrete because this is our way of things. So again, and I've mentioned this before, is that superstrings are just approximately twice as many orders of magnitude than the atom, 25 orders of magnitude small, and that Planck's length is 5 or 10 down from that, the atom, and then the superstrings are just down under that, like 50 orders of magnitude small. Still not a continuum mechanics, but it allows these effects that are beyond the Planckian regime, the trans-Planckian in the regime of things, floors under this attenuation of the effervescence of the electron, as it might be. These are mathematical models of the smoother and smoother with respect to the grain, because what has discretized the quantum, that in particle theory everything's a particle, in quantum mechanics these are waves, that it's a continuum mechanics. and that it's extra local, but the discretizing the particle is the fundamental of the local. The Einstein's relativity of special relativity is local, and Einstein's relativity of general relativity is extra local, and not necessarily non-local. But there is that it admits the Newtonian solution for gravity, where gravity always points to the source, not the image, which special relativity confirms is delayed from the source. So E equals mc squared is a formula, and its approximation is sensible. It was a result of kinetic energy equation. It's fungible. You only have to deal with the first term and not have to wonder about all the rest of the mathematical model left behind, the higher order terms. And it's tractable because then it can be applied to the energy of very, very small particles in very, very large bulks. It's famous too. So to begin to read, it says, chapter 11, E equals mc squared. In order to understand the law of the equivalence of mass and energy, we must go back to two conservation or balance principles, and here I frame these in terms of continuity laws, which, independent of each other, held a high place in pre-relativity physics. These were the principle of the conservation of energy and the principle of conservation of mass. The first of these, advanced by Leibniz as long ago as the 17th century, was developed in the 19th century essentially as a corollary of the principle of mechanics. There's a drawing from Dr. Einstein's manuscript. It illustrates pendular motion with a fixed length straight line rod connecting the axis of the pendular motion to the pendulum. Consider, for example, a pendulum whose mass swings back and forth between the points A and B. At these points, the mass m is higher by the amount h than it is at C, the lowest point of the path in height. At C, on the other hand, the lifting height has disappeared, and instead of it, the mass has a velocity v. It is as though the lifting height could be converted entirely into velocity, and vice versa. This is usually and often framed in terms of potential energy and kinetic energy. The exact relation would be expressed as mgh equals m over 2 v squared, with g representing the acceleration of gravity. What is interesting here is that this relation is independent of both the length of the pendulum and the form of the path through which the mass moves. This is related to ideas like the tautochrone, which is about taut things are rigid in the sense that something that's rigid is taut and doesn't bend, or it's otherwise always fully extended. And in time, the chrone and the measurement of time that they follow, and the pendulum in the form of the path through which the mass moves. The significance is that something remains constant throughout the process, and that something is energy. At A and at B, it is an energy of position, or potential energy. At C, it is an energy of motion, or kinetic energy. If this concept is correct, then the sum mgh plus m v squared over 2 must have the same value for any position of the pendulum, and it's 0. If h is understood to represent the height above c and v the velocity at that point in the pendulum's path. And such is found to be actually the case. The generalization of this principle gives us a law of the conservation of mechanical energy. But what happens when friction stops the pendulum? The answer to that was found in the study of heat phenomena. This study, based on the assumption that heat is an indestructible substance which flows from a warmer to a colder object, seemed to give us a principle of the conservation of heat. On the other hand, from time immemorial, it has been known that heat could be produced by friction, as in the fire-making drills of the Indians. The physicists were for long unable to account for this kind of heat production. Bumblebees can't fly, but they can. Their difficulties were overcome only when it was successfully established that for any given amount of heat produced by friction, an exact proportional amount of energy had to be expended. Thus did we arrive at a principle of the equivalence of work and heat. With our pendulum, for example, mechanical energy is gradually converted by friction into heat. In such fashion, the principles of the conservation of mechanical and thermal energies were merged into one. The physicists were thereupon persuaded that the conservation principle could be further extended to take in chemical and electromagnetic processes, in short, could be applied to all fields. It appeared that in our physical system there was a sum total of energies that remained constant through all changes that might occur. Now for the principle of the conservation of mass. Mass is defined by the resistance that a body opposes to its acceleration, inert mass. It is also measured by the weight of the body, heavy mass. That these two radically different definitions lead to the same value for the mass of a body is in itself an astonishing fact. According to the principle, namely that masses remain unchanged under any physical or chemical changes, the mass appeared to be the essential because unvarying quality of matter. Heating, melting, vaporization, or combining into chemical compounds would not change the total mass. Here, there's several times that Einstein really reflects a lot of expressed astonishment at the difference between weight and mass. And that's fair because on the Earth, everything has to accelerate to move around and establish uprightness, vis-a-vis that over the course of the Earth, the gravitational constant, 9.2 something meters per second squared, varies in the second and third decimal points, about that much over the course of the Earth. Some places it's even a little bit more. And it reflects that there's things to do with whatever is in regards to these floating things, and whether a spinning disk is lighter than a non-spinning disk, that these are the kinds of things that provide astonishment. Physicists accepted this principle up to a few decades ago, but it proved inadequate in the face of this special theory of relativity. It was therefore merged with the energy principle. Just as about 60 years before, the principle of the conservation of mechanical energy had been combined with the principle of the conservation of heat. We might say that the principle of the conservation of energy, having previously swallowed up that of the conservation of heat, now proceeded to swallow that of the conservation of mass, and holds the field alone. This is where efforts in unification are exactly for this goal, to reduce the number of moving parts and have the least number of fundamental entities that explain the most, as they might be the degenerate entities and have some laws about how they combine and then in their higher organizations behave as various organizations, or higher order terms, non-logical in the theory, or not fundamental in the theory, but yet elementary in their own theories and in their applications of domain and according to their laws. And so unification is quite a big thing, but then also what's to be watched out for is false unification. When something is really to be decomposed into its more utterly fundamental parts, or into two systems which are so complementary, which attain to each other, that's a difference between the dialectical and the square of opposition, and the fact that opposites each may have their own fundamental laws in terms of their relations to each other, vis-a-vis a foundation that is only in terms of one or the other, and would eventually run out and be incapable in terms of the other. So that's why when you think about whether the quantity of mass or the quantity of charge is fundamental, it's that fundamentally either can be considered fundamental, and that they're so related, these two either way, in charge. Because temperature is essentially a kinetic thing. It's vibration at the atomic level. Vibration in resonance in kinetics is just another thing above that, and then displacement and motion of things, and then higher order changes in displacement like acceleration and things. That's all just kinetic. And then for charge and all such matters of the electrical fields that have their flow, and the way electrons move, and the way in conductors, and the way fields generate potential, and when that reaches breakdowns or courses of conductance, these are the kinds of things that, whether charge or mass is fundamental, still has it, they're both quite fundamental, and then that in their fields is all together, they are yet all is interchanged by energy. The energy is this fundamental form of interchange, is of the events, but it might be seen as sort of a false decomposition to have it be utterly fundamental when those other two quantities, mass and charge, are so complementary and each fundamental, and also defined in terms of each other, in terms of electromotive potential and static and dynamic potential after kinetics of moments in charge, and the systems of energy. And why, for example, that entropy, the whole idea of the second thermal law, which is that everything just goes to rest eventually. And this represents a very, very, very classical law that what goes up must come down. That which rises falls. That which warms up will cool off. That it's that's a global phenomenon, but that in the local it could vary and be different. So with regards to this unification and description, it's an opinion. And when, for example, we have GR first and then SR from that instead of vice versa, this is where Einstein, the careful hedge, has picked a side and said it's SR first here and GR is closed, so, and I got nothing else to say. Everything else that comes out of it is mathematical. Back to the boss here, Einstein. Physicists accepted this principle up to a few decades ago, but it proved inadequate in the face of the special theory of relativity. It has therefore merged with the energy principle, just as about 60 years ago, the principle of the conservation of mechanical energy had been combined with the principle of the conservation of heat. Maybe prematurely. We might say that the principle of the conservation of energy, having previously swallowed up that of the conservation of heat, now proceeded to swallow that of the conservation of mass and holds the field alone. Conservation as of after that being of quantities of mass or charge. It is customary to express the equivalence of mass and energy, though somewhat inexactly, by the formula E equals mc squared. He really collects a lot in this. The hedge reveal, though somewhat inexactly, in which c represents the velocity of light, about 186,000 miles per second. E is the energy that is contained in a stationary body. M is its mass. The energy that belongs to the mass m is equal to this mass multiplied by the square of the enormous speed of light, which is to say a vast amount of energy for every unit of mass. But if every gram of material contains this tremendous energy, why did it go so long unnoticed? The answer is simple enough. So long as none of the energy is given off externally, it cannot be observed. It is as though a man who is fabulously rich should never spend or give away a cent. No one could tell how rich he was. Now we can reverse this relation and say that an increase of E in the amount of energy must be accompanied by an increase of E over c squared in the mass. I can easily supply energy to the mass, for example, if I heat it by 10 degrees. So why not measure the mass increase or weight increase connected with this change? The trouble here is that in the mass increase, the enormous factor c squared occurs in the denominator of the fraction. In such a case, the increase is too small to be measured directly, even with the most sensitive balance. For a mass increase to be measurable, the change of energy per mass unit must be enormously large. We know of only one sphere in which such amounts of energy per mass unit are released, namely radioactive disintegration. Schematically, the process goes like this. An atom of the mass m splits into two atoms of the mass m prime and m double prime, which separate with tremendous kinetic energy. If we imagine these two masses as brought to rest, that is, if we take this energy and motion from them, then consider together they are essentially poorer in energy than was the original atom. According to the equivalence principle, the mass sum m prime plus m double prime of the disintegration products must also be somewhat smaller than the original mass m of the disintegrating atom, in contradiction to the old principle of the conservation of mass. The relative difference of the two is in the order of 1/10 of 1%. Now, we cannot actually weigh the atoms individually. However, there are indirect methods for measuring their weights exactly. We can likewise determine the kinetic energies that are transferred to the disintegration products m prime and m double prime. Thus, it has become possible to test and confirm the equivalence formula. Also, the law permits us to calculate in advance from precisely determined atom weights just how much energy will be released with any atom disintegration we have in mind. Law says nothing, of course, as to whether or how the disintegration reaction can be brought about. What takes place can be illustrated with the help of our rich man. The atom M is a rich miser who, during his life, gives away no money, but in his life, in his will, he bequeaths his fortune to his sons, M prime and N double prime, on condition that they give to the community a small amount, less than 1/1000th of the whole estate, energy or mass. The sons together have somewhat less than the father had. The mass sum M prime plus M double prime is somewhat smaller than the mass M of the radioactive atom. But the part given to the community, although relatively small, is still so enormously large, considered as kinetic energy, that it brings with it a great threat of evil. Averting that threat has become the most urgent problem of our time. So this reflects on Einstein's contribution to the development of the atom bomb, although it was happening, and his expressive hedge is like, I am not responsible for the atom bomb, and it's a threat. So chapter 12 begins time, space, and gravitation. Now, a remarkable thing about relativity and quantum mechanics and physics writ large today is that the most theories of gravitation that involve objects pulling together, like Newton's gravity, violate conservation of energy, because nothing has a perpetual mobile. It can't be constantly working to pull two objects together. It would need energy to do work. Then, from my perspective, it's a fall gravity somehow. So instead, massy inert objects are just massy and inert, and they serve as to absorb just this totally residual, gradually vanishing result of a universal field called gravity, its force, and that this fall gravity arrives at why things fall apart. And it must be super classical, and various notions about the flux of gravitons would be even higher than, they're even more tachyonic than the flux of tachyons, like usual neutrinos or photons. And this is not new. After Newton, who invented gravity, this theory, Newton's gravity, and also who applied these various notions of after Galileo and all what came before him, as you can imagine, he was a very diligent researcher and not just struck on the head with his theories one day. That Newton's gravity is pole gravity. And so sometime after Newton's gravity, then some fellows came along like Fatio. And he's like, well, what if instead the immobile celestial spheres push in, and then particles, they're constantly flowing, or this wind of shadow or fall gravity comes in from everywhere at once and pushes things together. Well, this was argued that then that would be flux that would be, they were called ultramundane corpuscles. It's like, well, the universe is full already. How can it be full of gravity, this field everywhere? Well, it's space-time. It's space-time with gravity. And it results from basically that whatever is holding up the tent of three space dimensions is naturally falling back in. So if there's a question about where gravity goes, then lately in these days there's a lot of talk about, after superstring theory and stuff like that, there's notions of supergravity, and there's something like shadow gravity has also come about, because of course Fatio and Lesage were put down, and then later with the bringing out of relativity and general relativity and implementing a geodesy, and then just saying that space and time is curved, and so everything just goes straight. Well, what's down is like, down is just down. You know, what's down? It's like gravity says. It doesn't exist, but it's implemented as by Newton's inverse square law. And so for Fatio and Lesage, their theories are also, though, very well regarded as exploring this conceptually. And then the fall gravity is just the idea is, it's just like, well, it's just Newton's, it's just Fatio's and Lesage's, it's just super classical of that. It also happens to implement relativity's view of things, inverse square mass proportional distance times a constant for gravity. There are two usual constants of gravity: Earth, the terrestrial frames, and then G, just a value. That these days then, when they look out at far, far away galaxies, which are rotating and spinning essentially as in their own frame, but that none of their rotational force can affect us because they're too far away, that it drops off to just kind of linear and not inverse square, or it's like inverse cube or something like that. And that's called modified Newtonian dynamics. And all the satellites all about the Earth, including the GPS satellites and everything else, lives in an ephemeris, which is a keeping tracking of all the objects in the sky. It's from the Earth. And that's called the PPN, Parameterized-Post-Newtonian. And that has about 28 different factors, which are these higher level organizations, which also empirically happen to be cranked out every day by the Jet Propulsion Lab, which explain every single object's motion in its orbits around the Earth. this is the modern apparatus of the empirical, which supports such notions as global positioning satellites and the ephemeris of all vehicles and objects in orbit known about the Earth and beyond. Gravity in general relativity is down, and it's straight down, and that's great because it's simple, and it's then just that objects have their own relative velocity in this geodesy. They're always moving in their world lines, and every instant of the continuously divisible time, each one constantly immediately reevaluates to the rest of all the objects in all the universe of their potentials, which are above some floor that's any different from a uniform background radiation. So, chapter 12 begins time, space, and gravitation. There are several kinds of theory in physics. Most of them are constructive. These attempt to build a picture of complex phenomena out of some relatively simple proposition. The kinetic theory of gases, for instance, attempts to refer to molecular movement, the mechanical, thermal, and diffusional properties of gases. When we say that we understand a group of natural phenomena, we mean that we have found a constructive theory which embraces them. Theories are principles. But in addition to this most weighty group of theories, there is another group consisting of what I call theories of principles. These employ the analytic, not the synthetic method. Their starting point and foundation are not hypothetical constituents, but empirically observed general properties of phenomena. Principles from which mathematical formulae are deduced of such a kind that they apply to every case which presents itself. Thermodynamics, for instance, starting from the fact that perpetual motion never occurs in ordinary experience, attempts to deduce from this by analytic processes a theory which will apply in every case. The merit of constructive theories is their comprehensiveness, adaptability, and clarity, that of the theories of principles, their logical perfection, and the security of their foundation. The theory of relativity is a theory of principle. And it's a constructive theory. If it's not the one true theory, it's a bit of both. To understand it, the principle on which it rests must be grasped. And that says to understand it is to accept it. But before stating these, it is necessary to point out that the theory of relativity is like a house with two separate stories, the special theory and the general theory of relativity. Since the time of ancient Greeks, it has been well known that in describing the motion of a body, one must refer to another body. The motion of a railway train is described with reference to the ground, of a planet with reference to the total assemblage of visible fixed stars. In physics, the bodies to which motions are spatially referred are termed systems of coordinates. The law of mechanics of Galileo and Newton can be formulated only by using a system of coordinates. The state of motion of a system of coordinates cannot be chosen arbitrarily if the laws of mechanics are to hold good. It must be free from twisting and from acceleration and flopping. The systems of coordinates employed in mechanics is called an inertia system. The state of motion of an inertia system, so far as mechanics are concerned, is not restricted by nature to one condition. The condition in the following proposition suffices: a system of coordinates moving in the same direction at the same rate as a system of inertia is itself a system of inertia. This is the frame in the moving frame, or the frame as a moving frame. The special theory of relativity is therefore the application of the following proposition to any natural process. Quote, every law of nature which holds good with respect to a coordinate system K must also hold good for any other system K prime, provided that K and K prime are in sufficient movement of translation. This is that there's two frames. The second principle on which the special relativity rests is that of the constancy of the velocity of light in a vacuum. Light in a vacuum has a definite and constant velocity independent of the velocity of its source. Physicists owe their confidence in this proposition to the Maxwell-Lorentz theory of electrodynamics. Maxwell was a great electrician and great scientist about the electrical fields and the E&M fields, but other members of the electrical world also developed all the potential fields on the side. So there's a lot more fields, just like PPN, post-parameterized-Newtonian ephemeris for gravity. There has like 28 parameters. There's like about as many as there are letters of the alphabets, lettered fields of electricity and electromagnetism, which Maxwell's equations and for E and B have a particular neat closed form solution for electrodynamics than that with regards to Leonard Wishart and arriving the special relativistic course of the electron, that it is similar. Then back with regards to the two frames, that every law of nature would hold the goods, must also hold good for any other system K prime, provided that K and K prime are in sufficient movement of translation. If that's to be read that there are two frames and also two frames that are non-intersecting. This physics is an open system, so they still live in the same frame containing them. It's relative. Continuing, the two principles which I have mentioned have received strong experimental confirmation, but do not seem to be logically compatible, unless there's just one theory. The special relativity theory achieved their logical reconciliation by making a change in kinematics, that is to say, in the doctrine of the physical laws of space and time. It became evident that a statement of the coincidence of two events could have meaning only in connection with a system of coordinates, that the mass of bodies and the rate of movement of clocks must depend on their state of motion with regard to the coordinates, or proximity. You might also express that otherwise, if there's only a notion of near and far and not so much a notion of relation otherwise, that kind of reflects this notion of, well, how about line continuity and line drawing vis-a-vis the field continuity and coordinates in the Cartesian? Next paragraph. The older physics. But the older physics, including the laws of motion of Galileo and Newton, clashed with this relativistic kinematics that I have indicated. The latter gave origin to certain generalized mathematical conditions with which the law of nature would have to conform if the two fundamental principles were compatible. Physics had to be modified. The most noticeable change was a new law of motion for very rapidly moving mass points, and this soon came to be verified in the case of the electrically laden particles. The most important result of this special relativity system concerned the inert mass of a material system. It became evident the inertia of such a system must depend on its energy content, so that we were driven to the conception that inert mass was nothing else than latent energy. The doctrine of the conservation of mass lost its independence and became merged in the doctrine of conservation of energy. A body of mass in a frame is all the mass in the frame, and the sum of the charges, positive and negative, in a frame basically affect a sum. Those being quantities in their fields, where inert bodies that are massy and chargeless are not necessarily at all ever so affected by charge at all, except through the electromagnetic interface between charge and the electric field and gravity and the kinetic field via electromagnetism and magnetostatics. Thus, it's pointed out that Einstein is a careful hedge, is totally generous in providing a very solid opinion one way in terms of reading theory of relativity, which, as he describes it, is as a principle as vis-a-vis the empirical or the other. Physics had to be modified. The most important result of the special relativity system concerned the inert mass of a material system. It became evident that the inertia of such a system must depend on its energy content, so that we were driven to the conception that inert mass was nothing less than latent energy. The doctrine of the conservation of mass lost its independence and became merged in the doctrine of conservation of energy. The special relativity theory, which was simply a systematic extension of the electrodynamics of Maxwell and Lorentz, had consequences which reached beyond itself. Must the independence of physical laws with regard to a system of coordinates be limited to systems of coordinates in uniform movement of translation with regard to one another? It is. What has nature to do with the coordinate systems that we propose and with their motions? Although it may be necessary for our descriptions of nature to employ systems of coordinates that we have selected arbitrarily, the choice should not be limited in any way so far as their state of motion is concerned. That's a general relativity, theory of relativity. in statics, not relativistic dynamics. The application of this general theory of relativity was found to be in conflict with a well-known experiment, according to which it appeared that the weight and inertia of a body depended on the same constants, identity of inert and heavy masses. Consider the case of a system of coordinates which is conceived as being in stable rotation relative to a system of inertia in the Newtonian sense. The forces which relative to the system are centrifugal must, in the Newtonian sense, be attributed to inertia, but these centrifugal forces are, like gravitation, proportional to the mass of the bodies. Is it not then possible to regard the system of coordinates as at rest and the centrifugal forces as gravitational? The interpretation seemed obvious, but classical mechanics forbade it. The difference, a lot of times that's framed instead as like, well, there's centripetal forces, and the potential works out the other way. In the old swinging the bucket on a rope, and how does water stay in the bucket when you swing it over your head upside down? If you swing it with sufficient velocity and not with otherwise, that the rope becomes not taut and the bucket of water falls upside down. And so the true centrifugal is the idea of that you can't really have a true centrifugal if you have pull gravity, but if you have a fall gravity, there's the true centrifugal. Continuing, this slight sketch indicates how a generalized theory of relativity must include the laws of gravitation. An actual pursuit of the conception has justified the hope. But the way was harder than was expected because it contradicted Euclidean geometry. In other words, the laws according to which material bodies are arranged in space do not exactly agree with the laws of space prescribed by the Euclidean geometry. This is where, according to the geodesy, it can only move in straight lines along the course of the geodesy, and so nothing can ever turn around. It can never twist. It can never. You can't really have a 360-degree rotation because it would change. And so, for that to stay in Euclidean geometry, it's that the relativistic effects still have to exist insofar as that space contraction, but that then that there are just subspaces that exhibit their own frames, and it's called the rotating frame for the moving frame. So that then these systems are local systems that follow the geodesy and otherwise observe and obey passage in the geodesy in Euclidean space-time, in Minkowskian space-time, in Einstein space-time, with some special notions of frames. This is what is meant by the phrase a warp in space. The fundamental concepts, straight, plane, etc., accordingly lose their exact meaning in physics. There's a model as of over them. In the generalized theory of relativity, the doctrine of space and time, kinematics is no longer one of the absolute foundations of general physics. The geometrical states of bodies and the rates of clocks depend in the first place on the gravitational fields, which again are produced by the material system concerned. Thus, the new theory of gravitation diverges widely from that of Newton with respect to its basic principle. But in practical application, the two agree so closely that it has been difficult to find some cases in which the actual differences can be subjected to observation. As yet, only the following have been suggested. 1. The distortion of the oval orbits of planets around the Sun, confirmed in the case of the planet Mercury. Are the orbits taut? T-A-U-T, taut. 2. The deviation of light rays in a gravitational field, confirmed by the English solar eclipse expedition. 3. The shifting of spectral lines toward the red end of the spectrum in the case of light coming to us from stars of appreciable mass, not yet confirmed, he says. I'm not too familiar with that. If the shifting of spectral lines towards the red end of the spectrum in the case of light coming to us from stars of appreciable mass is why that's supposed to be why redshift is funny, or I'm not sure about that. It's kind of like one of those things I read one time. Is like, well, it's never been observed that there exists matter and antimatter, and that combining matter and antimatter releases all the energy from the matter-antimatter explosion that so results. But since then, there has been created antimatter in the laboratory, it's described, or systems that release such amounts of energy. Total energy conversion, total mass energy conversion. in very, very small quantities in totally contrived high energy magnetic bottles in national laboratories. And so the chapter comes to a close. The great attraction of the theory is its logical consistency and simplicity and clarity and applicability in many realms and generality. Not it's necessarily the fact of its decomposition to truly and utterly the fundamental. That's my part I put in. If any deduction from it should prove untenable, it must be given up. A modification of it seems impossible without destruction of the whole. Here, as we're discussing the pseudo-differential, the quasi-invariant, the degenerate points of degenerate intervals of points on a line, or the discretization, or particles and waves, Cantor's uncountable and Cartesian functions, the Gödel's incompleteness, are examples of things that are extra this way, while still having the regular fragment that's true in its domain and its application according to its elements, that otherwise that there are separations into other fundamentals that bring it together and emergent. That would as well leave it unchanged, just to the limits of its applicability. And then finally he closes with this great quote that I mentioned the other day about Newton. No one must think that Newton's great creation can be overthrown in any real sense by this or by any other theory. His clear and wide ideas will forever retain their significance as the foundation on which our modern conception of physics have been built. He's expressing that as part of the canon. His relativity is certainly part of the canon of physics. That then for Fabio and Lesage and what they call supergravity or fall gravity and this kind of unifications in their efforts, they have these as limiting in discrete and local and special cases. It's pretty clear. Well, that's the end of chapter 12. It's chapter 13 I haven't read yet. Let's see, well, I suppose I've gotten into it a ways though, but we'll get up to where he says some various cool things about the atomistic and the mechanical, and that we would get up to then these later chapters in the work about the fundaments of theoretical physics. Now I haven't even seen this really, and then that these end about page 120 and get into public affairs and his cause and this unseparated page and these nice things about the work. Well then, I hope that was pretty interesting, and it's part of something that is a really, kind of cool and relevant thing, because it's so great, It really is so great that something like relativity and the symbol course really was able to revolutionize the notions, and there's also about the fourth dimension otherwise, because the fourth dimension, is space and time. Time is the fourth dimension. But the whole other application, the notion of the fourth dimension back in this time, the Fantasiac turn of the 20th century, the 1905 to 1925 to 1945, was that the fourth dimension was a whole space upon which anything else could be possible. It was an entire vision of an outside world to our world. That the fourth dimension brought forth all these ideas of what could be made abstract, what could be made object, and so these are the kinds of things that really go into helping understand the time and the milieu of Einstein, and how at least he was able to get things relative at first, so that it was stricken from the absolute, but then to fit in with what he knew and learned about physics, and what he was able to find and make derivations that showed in the cusp of the moment that when the iron was once hot, that he could strike it, and and lay out in an academic work a foundation to help people explain physically and fundamentally something like nuclear fission and its energy, that these are the kinds of things that help us understand a lot what's going on in terms of these chapters from Einstein's book about the time, space, and gravity, which is basically his appreciation with regards to Newton's gravity and also with the Galilean, but then also, as was discussed, this properties and principles and theories. And then also this other chapter, E equals mc squared, about the quantities of matter and charge, and why energy is so fungible in our theories of potential that have transitions according to continuity laws, which also look just like symmetries and conservation laws, except they express how things change besides how they stay the same. Well, I hope you've enjoyed, because that's the end. Have a great day. Goodbye.